Let's test it out. Much better, right? Yeah, okay. We're in business. They coming. Thank y'all for being patient. Apologize for the inconvenience, but we have a expert expert interview, more like a Q&A, with Dr. Farrah. So I think that'll be fun. I might even drop the link and let the respectable ones join the platform. Okay. So they'll be in a minute. I'm just gonna let y'all jam out until everybody gets back on the panel. Thank you so much. Shout out to everyone in the chat. Appreciate your support. Yeah. Shout out to Gideon Block for them beats. What up, God Killer?
What's going on, G? What it do?
Killer. Please worry about the back end. We'll get it crack-a-lacking. Yes, I can hear you. Dr. Farrah, can you say something? I just want to make sure the audio is good.
Yeah, sure. I can hear you guys.
Oh, you're perfect. Anthony, just say something. I want to make sure the audio is getting clear.
Yeah, I'm here. Can you hear me?
Yeah, we're good to go. Few more minutes. I want a few more people to get back into position, and I put for 9:45, but we're going to start early, of course. Okay. Thank you. Dope. All right. What they call this the do-over show. But thank you and welcome to a special edition of Our Galaxy and Beyond. I don't know if it's a special edition anymore because how many times have you been with us, Dr. Farrah? This is like your third or fourth time, right?
It's about 3 or 4. Yeah, it's been great. It's always a pleasure to talk to you guys.
Awesome. We appreciate that. So before we get started, the God Killer, would you like to say anything?
No, I'd like to say first of all, I'd like to welcome Farrah to the channel. Appreciate you supporting the Pseudo Killers and all the work we do, and of course, it's a special edition when we have the great Dr. Farrah on.
Right, right.
Thank you.
Thanks. Anthony, would you like to say something before we get started?
I just want to say welcome everybody. Peace to everybody. Thanks for showing up. And thank you once again, Dr. Farrar, for answering the call and hanging out with us for a little bit. We appreciate it.
As I say, always a pleasure.
Right on. Bobby, if you don't mind, I was going to mute you out until you're ready to speak.
Yeah. Leave me out. I'm almost at the house too. Leave me out. Go ahead. I'm here.
Okay. Great. So, yeah, would you like to get things started, Anthony? Or I'll just jump into some questions. Dr. Farah, I want to preface by saying that some of these may be like repeat questions we had before, but some of these issues are still being questioned. So we just would like for you to reiterate and clarify if you don't mind, okay? And hopefully we have some fresh and new ones. If I can find my fresh and new questions, those are people. So I'll be on the hunt. I'll be on the hunt while we're doing the show. I'll let Anthony get started if that's okay with you, or I'll go ahead with a few, maybe new, maybe, repeat questions, but I think it's good to reiterate stuff.
Okay, yeah, I can start off, sis. Well, like I said, once again, thank you, Dr. Farrar, for coming on. And I guess I can start with the question that I sent you from me. It's got a lot to do with the CMB and how we detect it. Excuse me. But the question I have is, okay, the universe is expanding, and there's probably parts of it that we'll never ever see. Am I correct about that, or am I off a little bit?
You are correct, yes.
Okay. With that being said, we can detect the CMB, which is estimated, I'm guessing around 300,000 years after the Big Bang is what's
perfect.
How can we detect that when it's like the first light that we could, or radiation that we can detect, or the oldest, but there are things that happen after that that we'll never be able to detect visually, I guess. How can that be? We can look out and see the CMB all around, but there's, certain parts of the universe we'll never be able to see. So what am I missing right there?
Okay, so let me first say, if anyone wants to interrupt me or stop me, please do, because I tend to ramble, but I tend to ramble especially when people ask like really quite deep questions, and that's a deep question. I can't give you a complete answer to it in probably the time we have, because I might need to go on for several hours. But let me give it a try. Okay, so let me first explain a little bit of terminology. So in astronomy or cosmology, there is this idea called a horizon. And so you'll hear astronomers or cosmologists talk about a thing called a horizon of some kind. And there's actually quite a few different horizons in cosmology, but they all basically boil down to being the same sort of idea. And it's actually kind of quite simple. It's just the furthest distance you can see. So, for example, if you go to whichever ocean you happen to be closest to and you look out to sea, you're probably familiar with this idea of like what's on the horizon. You know, you see the sun sink below the horizon, you see a ship coming over the horizon. The horizon, when you look out to sea, is as far as you can see, and it's because the Earth is curved and you can't see any further than the curvature of the Earth allows you to see. So it's a limit, a sort of a fundamental limit on how far away you can see something. In astronomy, or when we talk about the universe, there's, as I say, there's a few different ideas of horizons, but I'll talk about one in particular, and it's the one that's related to the CMB, or the cosmic microwave background. And to explain this, I have to give a little bit of history of the universe, that is. In essence, when you have, oh God, sorry, I can't talk this afternoon. The way we understand the universe is by this model called the Big Bang model, where around 13.7 billion years ago, the universe started off very hot, very small, very dense, and then expanded really, really quickly. And there's an awful lot, and that's where the idea of the expanding universe comes from. You know, you start with this tiny, tiny little universe. It's sometimes, if you go look in older books, called the primeval atom, because it's just expected to be this tiny little thing, and then expands really, really quickly. And it expands quickly to begin with, and then as time passes, the expansion rate slows down, but it's still expanding. Okay, this is where things get a little bit tangled. In the very early universe, when it was very hot, very dense, everything that we see today was much, much closer together, and by and large, a lot denser, a lot hotter than we see it today. Now, okay, if you look up into the sky and you see our sun, it's incredibly hot and incredibly dense, but the space between stars is really, really empty and really, really cold. So on average, the universe today is a pretty cold, pretty diffuse place. You know, there's a lot of empty space, a lot of cold space. When the universe was very young, that wasn't true. And when the universe was in that state, when it was very, very young, everything in with the universe was so hot and so dense that none of it existed as normal atoms. They existed as ions, which is when one or more of the electrons in the orbiting the nuclei of atoms are stripped away. And to kind of not delve into an awful lot of quite complicated physics, when atoms are ionized like that, when they've lost a few electrons, when they have some charge, in other words, they interact really, really well with photons. And when they're neutral, when they have a full, all the electrons they're supposed to have, they don't interact anything like as well with photons. So what that means is that when the universe was very, very young, you had this sort of soup, this sea of ionized atoms and photons all bouncing around madly together, interacting strongly all the time. Typically, a photon would go a really short distance, encounter an ionized, an ion, interact with it, change direction, change energy, zoom off in another direction. Shortly thereafter, it would encounter another ion, it would interact with it, it would change its direction, it would change its energy. All of the photons in the universe, when the universe was very young, were doing that all the time. However, as the universe expanded, it also cooled. And as the universe cooled, you eventually get to a point where the ions in the early universe, everything has cooled down enough that those ions can recapture electrons and become neutral atoms. And that is a critical point in the universe's history. It's given a name, it's so important. It's called recombination, where you recombine your ions in your electrons to form neutral atoms. And when that happens, something rather special happens, because all those photons that were bouncing around previously most of the universe was ionized, those photons interacted really, really effectively with those ions. They couldn't go far at all before they interacted, changed energy, changed direction. Now, all of a sudden, the universe is largely neutral. And what that means is that photons no longer interact anything like as well with the now neutral atoms. And what that means, sorry, you asked a deep question, you kind of got me on a roll here. What that means is those photons suddenly can travel immense distances before they have any chance of interacting with anything. So you have this kind of sea change, if you like, in how light travels through the universe. Before recombination, about 300,000 years, as Anthony correctly said, photons bounce around crazily, interacting with everything. But as soon as this stage happens, they suddenly hardly interact at all. And what that means is, in effect, those photons, as I say, they can go huge distances without interacting with anything. And that means that when we detect those photons on Earth with a telescope, we see the last thing that they did, the last interaction they did. And this is why, if we look at this particular wavelength, the cosmic microwave background, so you're looking at microwave wavelengths, you're essentially seeing the last thing these particular photons did in the very, very early universe, the last interaction they had with this sort of primordial plasma before that plasma cooled enough to become neutral, and the photons zoomed off into the universe, unable to interact with anything anymore. If you want an analogy for what this is like, you could sort of imagine a photon, a particle of light, bouncing around inside a cloud. And in that cloud, there's lots of water droplets floating around. The photons will sort of bounce around off the water droplets very, very frequently. But as soon as they get to the edge of the cloud and come out of the cloud, there's vastly less water droplets to interact with. And those photons zoom off across the sky perfectly freely. They're not doing anything anymore. And so what that means is that if you're on the ground and you look up at a cloud, on one level, you're kind of thinking, hey, that's a pretty cloud. But what's happening on a sort of physics level is you're seeing the outer edge of that cloud, because that's the last interaction that photon had. Now, if you got in a hot air balloon and went up into the cloud, you would see hardly any distance at all, because those photons that you see when you're inside the cloud have just bounced off a water droplet very, very close to you. And so you can't see, more than a few feet. It's the same idea with the universe. Before the cosmic microwave background forms, it's like being in a very hot, very dense cloud. And as soon as the universe cools down enough to allow atoms to form, to become neutral, it's as if you are coming out of that cloud. And so your photons stream freely across the universe. This is why astronomers call the distance to the formation of the cosmic microwave background a horizon, because it's the furthest distance you can see. That's kind of the first part of the question. The second part of the question is really quite a deep one, and I can't really do more than scratch the surface here. Strictly speaking, when we do astronomy, when we do cosmology, astronomy, whatever branch you want to call it, what we are doing is studying what we can observe. So when we talk about the universe, we're really talking about the observable universe, the things that if we get a telescope and say, okay, let's look up into the sky and see how far we can see, you're essentially saying that the universe is what you can see through that telescope. And if you look at it that way, the cosmic microwave background is the furthest, the most distant thing you can see, but it's the most distant thing in time as much as it is in space. Because if you kind of think about it, where was the CMB formed? Where did you create the cosmic microwave background? Well, you actually create it everywhere at once. So where you're sitting right now, where I am sitting right now, right now it's 13.7 billion years after the Big Bang. Everything's, well, relatively cold. I mean, the sun was quite hot today in the West Coast, but, we live in a cold, very sort of almost empty universe. But if you wind the clock back 13.67 billion years, well, a bit more than that, and you just go back in time, but you stay exactly where you are now, then if you wind the clock back all the way, the CMB photons were being formed right where you are sitting now. So when people say the CMB is as far away as you can see, what they're really saying is that it's as far back in time as you can see. The other sort of the extension to this, and I promise I'm nearly at the end, the extension to this is, of course, when people say, are there galaxies out there that we can't see yet because their light hasn't reached us? That's a really, really deep question, because on one level, you might say, well, sure, there must be, right? I mean, the universe can't just be everything that we can see. There's got to be stuff further away than that. The universe can't just be the patch of the sky that we observe. I would say that's probably true. The trouble is, we don't have any way to even in principle know that, because we have no way of observing it. We have no way of getting that light to us, because the speed that light goes is the speed limit of the universe. So this is why some astronomers will say we study the observable universe, because that's as much of reality as we can be sure exists. Now, okay, sure, there's probably more out there, but we can never know about it because the light from those parts of the universe can't reach us. And so the answer is always going to be, well, I don't know what's out there. Maybe what we can see is all that there is. Maybe there's much more out there. Maybe we're a small little patch floating in a much, much bigger ocean. Both of those things could be true, but we have no way of knowing.
Great explanation, Dr. Farrah.
Yeah, that was great.
And I wanted to say, like, here, I don't really want you to like dilute your answers. I really want you to go in and give us everything you got. If it's not too exhausting for you, like, we can take out our pen and our pad, and if we don't get through all our questions, then you're like the resident astrophysicist. We'll just ask you back when you have time. Okay.
Oh, totally. I'm happy to go into detail, and I will always make time for you guys.
Thank you. We so appreciate that. You just don't know, really. I'm going to ask a question, and then I'm going to hand it off to Barrick, because he's probably the one. There's maybe one more in the chat that really, besides Anthony, that has a good handle on some very complicated concepts. So I'm just interested to see what his questions are going to be and how you're going to answer, for sure.
Totally.
But I know that you're not going to, like, go off on something. You're just going to simply say, I don't know. And we love that. We try to tell the community that's how it is. But we're just going to keep pressing it. I don't know what I want to ask first. I think I'm going to start with this, because this is a little tricky. I probably know what your answers would be, but still. Is the Big Bang the true beginning, or just a phase in a larger cosmic cycle?
Oh, wow. Start with the simple stuff.
Yeah, of course.
I'll give you the short answer. And actually, this one I have to give a fairly short answer to, because
that's fine.
It's for reasons that will become apparent. So the short answer is, I do not know. The longer answer is, or the slightly longer answer is, nobody knows.
Right.
But let me kind of qualify that a little bit. So, and I'll maybe try and give a historical perspective for this one. So
Absolutely.
since astronomy really became a discipline, a scientific discipline, this sort of one of the big questions has been, well, where did everything come from? How did the universe get here? And if you kind of reduce this down to the last, say, 150 years, maybe 150, 200 years, up to about 1963. Oh, wait a minute, was it 63? Yeah, 1963, I think. There was a big debate in the scientific community, in the astronomy community, between two competing ideas for how the universe came to be what it is, what we observe today. One of those ideas was the Big Bang theory, which essentially just stated the universe began at a finite amount of time in the past and then started really small and expanded. And then the competing theory was called the steady state theory. And the steady state theory said the universe has existed more or less in its current form with expansion forever, that there was not a beginning. And this obviously raises a whole bunch of questions, like how can you have a universe that expands forever and always looks the way it looks now? Answering that question would take about 2 hours and would involve me getting out PowerPoint slides. I'll happily do that another time if people are interested.
Yes, I think so. That'd be great.
But for now, I would just say, just for the sake of this question, maybe take my word for it that it is possible. However, this debate only really lasted until 1963, because in 1963, a discovery was made, actually the cosmic microwave background that Anthony mentioned earlier, which kind of sealed the deal. It kind of said, at some point in the past, the universe must have been way smaller, way denser, way hotter than it is today. And that point in the past must have been a finite time in the past, and it can't have been, in at least cosmic terms, all that long ago. And that really kind of sealed the deal, and the steady state theory, basically died the death of the dodo, and the Big Bang theory emerged triumphant. However, that left, this is as with all things in science, as soon as you answer a question, 5 new questions pop up.
Yes.
The problem with, or not the problem, but the questions that the Big Bang theory raised would be things like, why was it this amount of time ago that the universe was born? Why is it that the universe expanded in the way that it did? Why is it that the universe today is this vast, enormous place? Isn't that a sort of rather profligate display of whatever created the universe to, or whatever made the Big Bang happen? And these questions, we don't yet have anything like a good answer to. So there are numerous reasons for this. Observationally, it's very difficult to get constraints on what was going on when the universe was much younger than it is now, because everything is it's just a long, long way away. It's really, really faint because the light has traveled across most of the universe and therefore gotten rather diluted. And this is why telescopes like the James Webb Space Telescope, which is the most advanced telescope we have ever built, it's specially designed to look into the early universe. It's got special detectors. It's optimized to work at what astronomers call near to mid-infrared wavelengths, which is wavelengths of round about 1 micron to about 30 microns, which is longer than human beings can see. But for various reasons it would take a while to get into, those wavelengths are very, very much optimal for seeing galaxies when the universe was very young.
Okay.
However, there's a limit, and that limit, and this is a great ordering of questions, by the way, is the formation of the cosmic microwave background. Just as when you look at a cloud, you can only see the outside edge of that cloud. You cannot see in it because the light is scattering around too much. With ordinary light, you cannot see further back in time than the cosmic microwave background, which immediately sets a limit of saying you cannot get data more than about 300,000 years after the Big Bang.
Mm-hmm.
Now, there are potentially ways to overcome that limit. Neither of them are practical yet, but they may well be.
Okay.
One of them is to use gravitational waves, where you are not limited by the cosmic microwave background. You can see a lot further back. And the other one is to observe particles that are not light. They're not photons, but to use a different type of particle to observe with called a neutrino. And both of those methods in principle could let you see a lot further back than the cosmic microwave background. The trouble is we don't yet have telescopes that can do that. They would be expensive. We have still working out the technology to build them. It's going to be another probably 20, 30 years at least until we have telescopes like that. I mean, maybe I'm being pessimistic there. So the problem then is we don't have much observational experimental evidence to kind of tell us how might things have happened. And so we have to essentially just sort of say, well, the CMB is our best constraint. Let's see what theoretical models are consistent with the formation of the cosmic microwave background, the subsequent expansion of the universe. And the trouble with that is that there's an awful lot of unknowns, a lot about what we observe about the universe still doesn't really make a great deal of sense to us. So, for example, there's this idea of dark energy, which makes the universe nowadays, the last sort of half of its history, start to expand faster and faster. We still have really no good idea why that is happening. There's no good theoretical model for that at all. And that makes working out what the Big Bang was, why it happened, what caused it, was it the beginning of everything? Was it just an event in a much, much larger space-time, if you like? It makes that question currently impossible to have a good answer to. There's lots of speculation. There's lots of ideas. There's plenty of models out there that say, here's a way that you could have a much bigger space-time, a much bigger multiverse, for lack of a better word,
right,
in which something happened and it caused a little pocket of that universe to kind of, again, for lack of a better word, to explode and to have a huge creation of new particles which became the galaxies that we see around us today. Now, there's all sorts of issues that such models have to deal with, most notably being, well, if you're going to have a much bigger space in which our universe formed, then what made that much bigger space? And so you always kind of run into issues like that. And so there's no real agreement in the community as to which model is correct. But I don't think there are going to be meaningful constraints, meaningful ideas about what happened before the Big Bang, if there even was a before the Big Bang, for probably quite a while, just because it is such a difficult thing to observe and study.
Fair enough. Real quick though, I don't know if they were serious, but this is a pretty intelligent dude. So I'm going to ask you to either answer yes, no, I don't know to this one. Okay.
Sure.
I'm just entertaining the chat. I wanted, to make it interactive and give them an ability to participate also. Okay.
Sure.
So Posterius Thought asked, has Eric Weinstein figured out the theory of everything? I think he was being funny, but
has Eric Weinstein figured out the theory of everything? I'm going to cheat and I'm going to say, strictly speaking, I have to say I don't know, because I haven't looked at what he's proposed. I've got to admit, I am strongly suspicious the answer is no, but I'm not
Okay.
willing to say it because I haven't looked at it.
Got it. Thank you. Thank you for entertaining that question.
Oh, no problem.
Unc, would you like to say something before I move on to Kent,
I,
and then I'll go to Barrick?
I just wanted to ask the question. Uh, I just want to. Matter of fact, that answer you gave, that was very educational right there.
Yes, it
Oh,
was.
thank you.
Yeah, you did a great job at that. It wasn't too complex.
Mhm.
I'm gonna say it wasn't too complex for us. I'm not quite sure the people that follow us they could get it, but you told the story of the universe. I really appreciate the way you did that. And I was saying, okay, I'm in the cloud. I get it. The iron is bounce. Okay, I got you.
Right, right,
But
right.
yeah, so I could, and you gave it 2 parts to it. Yeah, that was love right there. I appreciate that.
Oh,
Listen,
thank you.
I just get a lot. I'm gonna clip that.
We
That's deep
are.
right there. But I wanna take us back to a world where early hunter gatherers. I'm not sure if uh Anthony, space age African. I don't know if he prepped you for this question, so I'm not sure where you at, but I know you'll let me know. So early hunter gatherers, when they start to produce their astronomical, and I'm using that word loosely, they devices, for agriculture and stuff like that. I think we would call that wasn't quite astronomy, maybe proto astronomy or something like that. Okay, so there's astronomy, there's astrology. Based off your expertise, which came first, or was it intertwined? And could the people of that day know the difference? Did they really know the difference? I know what my answer was. I'm not gonna say what my answer is. I want to hear what your answer is.
Sure. Okay, so I'll have to preface this by saying this is not an area that I study for a living. I think to get a good answer to this, you would need a cultural anthropologist.
Okay.
But at the same time, I'll still give it a go because
Okay.
I think that's a really fascinating question and a really, really deep question. I'll give you my perspective, but as I say, I'm not an expert on this.
Appreciate that.
Okay, the headline would be, I think they have been deeply intertwined for most of human history. And I think that they have only really diverged in a substantial way in the last 3, maybe 400 years of human history. I think up to that point, and especially the period you mentioned when, early hunter-gatherers, I think those two things were so closely intertwined that they were almost inseparable. And this is where I get into a regime of not knowing all that much, but I'll give it a go. My impression is that since the sort of earliest humans, the earliest Homo sapiens, humans have looked around them and simultaneously had two thoughts. One of those thoughts is, why am I here? What is existence? What is thought? What is consciousness? Why do things exist? The deep questions, the spiritual questions. And at the same time, especially early hunter-gatherers, they were wondering, how do I not freeze to death? How do I not starve to death? How do I not get eaten by a lion? Stuff like that. And so if you look at, or at least from my hazy memory of these things, and please bear in mind, my memory of these things is going to be very much the sort of the Western history, because that's what I grew up with. But obviously this happened everywhere across the world. If you look at kind of how cultures across history have tried to answer those two questions, for the vast majority of human history, they tried to answer them together. So it's interesting you mentioned early hunter-gatherers, because I remember reading a long time ago about something I thought was just one of the most brilliant things I've ever heard of. And it was tales about how tribes in, I don't remember where in Africa, but it was somewhere in Africa, many thousands of years ago, worked out that they should time the seasons when they planted crops according to the alignment of the crescent moon. And when the crescent moon was at a certain alignment, that was a good time to plant. And when it wasn't, then they shouldn't. And they worked that out because, well, if they planted at the wrong time, they basically all starved, and if they planted at the right time, they had plenty of food. There was a sort of survival imperative. And that kind of thing is a neat example of really scientific, logical thinking. But at the time, they would have wrapped that idea up in spirituality, in sort of cultural narratives, in religion, if you like. And this has gone on throughout history. So if you turn to someone who is often regarded as like one of the first ever true astronomers, it was a guy called Ptolemy, who lived in Alexandria in Egypt, I believe, around about 2,000 years ago. He is famous in astronomy circles because he wrote the first ever kind of astronomy book, which laid out the geocentric model for the solar system very mathematically. I mean, it's a model that we now know isn't right, but at the same time, it made very good predictions. He based his model on sound mathematical reasoning. And so for that reason, it's thought of as an astronomy book. The thing is, though, Ptolemy, almost in the same breath, wrote a large book on astrology, where he talked about fortune telling, divination, seeing the future by looking at what goes on in the stars. This has gone on, as I say, from as far as I know, for most of human history, even up to people like Kepler and Copernicus and Brahe, who, at least in the Western world, were instrumental in ushering in the heliocentric revolution. Even they dabbled in astrology a little bit. I mean, in some cases, just to make some money on the side, but they still did it. I don't quote me on this, but I think Kepler, when he was young, before he became Tycho Brahe's assistant, and he actually did some fortune telling to make money. So I think it's really the scientific revolution, the Renaissance, as they call it in the Western world, is where astrology and astronomy really started to diverge very heavily, when scientists sort of realized, well, hey, hang on a minute. There is no sort of divine predictive power in this. You cannot read the future in the stars. You cannot tell someone's personality from the day and time and place that they were born, but you can use mathematical models to understand why things move in the sky in the way that they do. And I think that divergence kind of started maybe about 1500, 1600, and took about maybe 100, 200 years to happen fully. But certainly I would say by 1700, 1750 maybe, the split was complete. And at that point, astrology and astronomy were considered completely separate subjects.
That's a great answer. And I would have answered it just like that. See what I'm
excellent.
saying? See?
Oh,
I knew. I just wanted to, because, when we actually having these conversations, we talk about like modern science and proto science. And the thing that you spoke of is when things start to actually separate. I always say that humans couldn't get out their way by always trying to mix their spirituality together. And I always say 350,000 years. That's the hardest thing for us to actually do. And like you said, even when I think you said the Greek guy who was the Ptolemy, you said even when he wrote strictly a treatise on that, he still had another book, right?
Oh, yeah.
Or I'm gonna do this and make some extra money off of it. And that's interesting that you said that. I appreciate your answer. Matter of fact, they do the same thing with medicine. The Edward Smith medical papyrus, where the Egyptians had these first texts with rational thought on different cures or different on medicine and how to reach certain conclusions. And they was at that point they was trying to separate, but like you said, it takes time. We appreciate that question. I just wanted to bring us back. We was in the cosmos. I wanted to stand on the ground and look up at the cosmos for that answer.
Absolutely.
Very good. I'm gonna move to Kent. Kick down low, Little Killer Official.
Hey, what's going on? How y'all doing tonight?
Good.
Y'all can hear me?
Yes.
Yeah,
Loud and clear,
Loud
bro.
and clear.
Okay, how you doing, Dr. Farrah? Glad to have you with us, man.
I'm doing great. How are you doing?
I'm pretty good. I had a question about. I'm not sure if Anthony already went over this early in the show. A lot of times people get black holes confused with like planets because when you look at it, it looks like a black dense planet, and that's the gravity can't escape it and all of that. But I learned that it was like a region, like a dense region or something like that. Can you explain that for me?
Sure. Okay, so I'll first say you guys ask all the really deep, very difficult questions. This again is a topic I can go on for hours about because this is something I actually do study research-wise. So again, if I'm just rambling on, please do stop me. Okay, so the question, what is a black hole, is really not a simple question to answer. I will try and give you the kind of the deeper perspective on it. And again, it involves being somewhat historical about how I answer it, just because I think that historical perspective kind of helps. Okay, I'll give you the headline first. The headline is black holes are objects that we know exist out there in the universe, but we don't know really what they are. They are one of the, if you wanted to list the sort of 5 greatest mysteries of the universe, what is a black hole would be one of those mysteries. We don't have a good picture of them yet. We have some pretty good ideas, but those ideas are not yet confirmed. Okay. The longer answer would go like this. Round about the time when humans first developed telescopes, they were also developing the first sort of proper theory of gravity, Newton's theory of gravity. And obviously, people being people, they decided to play around with this idea and do thought experiments, see what they could come up with. And the idea of how gravity works and how, why you have gravity on planets, and if you throw something into the air, it comes back down again. Lots and lots of experiments and theoretical studies were done based to try and work out how all this happens. And one of the thought experiments they did was, well, okay, let's calculate this thing called an escape velocity. How fast you need to go to completely get away from a planet. And that was all done. And then someone had the idea of saying, well, the thing that moves the fastest is light. Nothing can go faster than light. How big would something have to be, or how massive, would it have to be for it to not even let light escape? And that's kind of where the phrase black hole first came from. It was actually quite a long time ago, and it was just some people having this idle, coffee time conversation, basically, over, if you wanted something to be so big that not even light could escape, how big would it have to be? And it was just a theoretical idea. And then fast forward about 100 years, Albert Einstein came up with the next theory of gravity, his theory called general relativity. And in a different sort of way, and again, this would be a couple of hours digression, so I'm sorry I can't go into this, maybe another time if you guys are interested. But the same thought experiment came about. What would happen if you had an object where it was so massive and so dense that not even light could escape? And this would have been round about the year 1915, so shade over 100 years ago. And even back then, it was still just a completely theoretical idea. No one thought these things actually existed because they did some calculations and they were coming up with just seemingly crazy numbers. They were saying, well, okay, let's say you wanted to take our sun and you wanted to make it so that not even light could escape from it. What would you have to do to it? And the answer came back from Einstein's theory that you'd have to compress it down to being like a mile across, maybe 2 miles across. And when you consider that the sun is many times the diameter of the Earth, it's like, okay, that's this crazy town, or it sounds like it. And if you do the same calculation for planet Earth, if you said, how much would you have to squash the Earth until not even light could escape from its surface, the answer you get is about the size of a golf ball. And so, it just sounds nuts, right? You'd have to compress everything on Earth and within Earth down to the size of a golf ball. That's not realistic. But, scientists like to play theoretical games because it's something to do. And so this was explored in some detail. That sort of progressed in that way until around about 1962. And in case you're thinking, hang on, that sounds like quite a similar date to when the CMB was discovered. Yep, that's right. The early 1960s were like revolutionary in terms of what happened in astronomy. We made multiple discoveries that just changed everything that we understand about things. But in the early 1960s, astronomers built the first decent X-ray telescope. That is, a telescope that observes in X-rays rather than normal optical light. And just in case anyone's not familiar, of course, X-rays are light, but they're light that has considerably more energy than optical light does. And so what happens if you observe in the X-ray, if you build your telescope such that it's sensitive to X-rays rather than optical light, what that means is that you tend to observe processes that are extremely energetic, much more energetic than processes that produce optical light, because optical light has a certain amount of energy. X-ray light has considerably more energy, so you are tracing processes with X-ray telescopes that just have considerably more energy. And when astronomers used this new X-ray telescope, they discovered a truly remarkable object. And that object has the name, and I'll tell you the name, and then I'm going to tell you why it's not as cool as it sounds. The name of this object is Cygnus X1. And that sounds pretty good, but when you kind of pick it apart, it's actually just astronomers naming things quite sensibly, because this object is in the constellation of Cygnus. It's an X-ray source, and it's the first X-ray source that was discovered. That's literally what the name means, Cygnus X1. It's kind of boring when you break it down like that. The reason this object was so weird, though, was that it was giving out enormous amounts of X-ray light from a really, really tiny region, like a minuscule region, like maybe a few million miles across, which in astronomy terms is nothing. And the trouble with this, the reason this was so problematic, is that there was no known process in astronomy that scientists were familiar with that could produce that much energy from that small of a volume. And so astronomers had to hunt around for things that could do this. Like, what possible mechanism is there to create that much energy in that small of a region? Now, this is where this would get quite difficult to explain unless I had like considerably more time. But the only way that you can do it, at least that we are aware of, is if you have something falling into what had up to then been a completely theoretical object, namely a black hole. And that sounds completely counterintuitive, but the logic goes like this. You have something, you have your black hole, and something starts to fall towards it. And when it's far, far away, it's not moving at all. But as it falls towards the black hole and towards the black hole, it starts going faster and faster and faster. And as it goes faster and faster and faster, it gains what physicists would call kinetic energy, which is energy of motion. And if some fraction of that kinetic energy, that energy of motion, can be harnessed and turned into light, then that light will radiate away, because it's much harder for light to fall into a black hole, and that's the light that you will see.
Right.
And if you want an analogy of this, it would be like saying, well, let's say you get in your car and you back out of your driveway, you're doing like 2 or 3 miles an hour, and you bump into, the side of the wall as you're backing out. You might scratch your paintwork a bit, but that's all you will do, because you're moving slowly. Your car doesn't have much energy of motion, and therefore you won't do much. But if you're doing 80 on the freeway and hit the sidewall or something, you're going to wreck your car, because your car's going much faster. It's got much more energy of motion, and therefore much more will happen. It's kind of a weird analogy, but it's the similar sort of idea. If stuff falls down towards something, then if you can harness some of that energy of motion and turn it into light, that light will radiate away. And the further the object can fall, the faster it can get, the more energy that it can release. And so, for example, let's say, wherever you are now, you just pick something up, nothing valuable, and hold it above the ground and drop it. By the time it hits the ground, it's not going to be going terribly fast. You'll hear a bit of a thump, and that's it. But if something can fall far further than that, then as it falls, it gets faster and faster. It gets much more kinetic energy, and therefore it has much more energy that it can turn into light by whatever mechanism and radiate away. The Cygnus X1, this X-ray source, was giving out so much X-ray light that the only way that astronomers could think of that you could generate that much X-ray light from that small of a region was if there was some insanely, incredibly compact and dense object there that stuff was falling towards, gaining lots of kinetic energy, and some of that kinetic energy was being converted to light because it has lots of energy. That light would be X-ray light, and that's the light that we observe. There was literally no other way that astronomers could think of that you could do this. And so all of a sudden, this theoretical object called a black hole that Einstein and other people like Schwarzschild had written about to each other, just thinking, this is just complete theoretical, we're just having ideas and playing around with things that can't exist. All of a sudden, astronomers were saying, hey, you guys, do you mind if we use this? Because we can't think of anything else that could do this.
Right.
And so you have this kind of weird situation where there are objects out there in space, and we know about lots of them now. There's black holes everywhere. They're not as common as stars, but there's plenty of black holes in the universe. Where
even in our solar system, not solar system, in our galaxy.
Yes, there's quite a few in our galaxy. There's I'll give you the distance just in case anyone wants to know. The nearest black hole to our solar system is about 1,500 light years away. So a long, long way. Like
right.
There's nothing terribly close to us. But yes, there are black holes in our galaxy. There's an extremely big black hole at the center of our galaxy.
Sagittarius A.
That's the one. Yes, spot on. And the reason I say so, I'm aware I'm starting to ramble because you're getting onto black holes.
No, you good.
I like them.
Breaking it
Ramble
down.
right? Ramble on.
I'm following
sure.
you. I'm following you.
Facts.
Well, in that case, let me try and give a brief sort of overview of why black holes are so weird. First of all, they're definitely out there. They have to be out there. The evidence that out there are these incredibly compact, incredibly dense objects where they cannot be any kind of planet, they cannot be any kind of star, just because the amount of energy that is generated when stuff falls into them is way too big. The evidence that they exist is overwhelmingly strong. The trouble is trying to explain what these things are, like what is a black hole, answering that question. And that question is not answered yet. The the reason for this is we don't yet have a good theoretical understanding of what happens when you compress matter, when you compress stuff, atoms, stuff made of atoms, if you like. What happens to that when you compress it to incredible densities? In essence, the densest objects that we know about and that we kind of sort of understand are objects called neutron stars, where it's still an incredibly dense and compact object, but in essence, it's a very small object where the object's density is about the same as an atomic nucleus. So this isn't really correct, but you could think of a neutron star as a single object that's like of order 5 kilometers across, where the density of the object is about that of an atomic nucleus. And we sort of understand those. You can do experiments in laboratories to understand how atomic nuclei work. There's still a lot of mysteries about them, but you kind of can go, okay, I've got a handle on this. The trouble is we don't know, or we don't have experimental evidence for any state of matter beyond that. So atomic nuclei, the reason they stay up, the reason they don't collapse is because you've got a force. It's a force that physicists call the nuclear force that supports atomic nuclei against essentially collapsing in on themselves. Once things get so dense that even the strong force, the nuclear force, cannot keep things up anymore, then we don't have any idea what's really going on. There's no model, there's no good theoretical model for it. And so what that means is that if you try and write down equations that describe how a black hole works, you're entering interesting regimes. You're entering regimes where we don't have a good handle on what's happening. And that means you start to get what I'll just describe as weird stuff happening in the mathematical descriptions. So the most popular mathematical description for a black hole is a model called the Kerr model, Kerr. And it works really well when you're looking at outside of a black hole. And it's been tested. It hasn't been shown to be exclusively true. I mean, it seems to work quite well, but it hasn't been sort of thoroughly tested, just because doing so is observationally very difficult to do. But this model makes some predictions for what happens inside black holes, which are downright freaky. And it's all of those things that kind of, you read about, or in science shows they'll talk about things about a singularity in the center, which is a point of what some books will call infinite density. There's a collection of those predictions that this particular model makes, which are very, very difficult to reconcile with other branches of physics. So, for example, a singularity to a physicist means the theory is broken at that point. Something there doesn't work, because what effectively happens at the singularity is, in the math, you have a divide by zero. And, we've all been taught in math class, you cannot divide by zero. It's not mathematically allowed. Now, some people will say, a divide by zero just means it's infinite. And they'll start saying, well, you have an infinity there, and start using the mathematical idea of infinity. The trouble is that's kind of a debatable thing to do, because there's various ways you can define infinity. But ultimately, you shouldn't be dividing by zero. If you get a divide by zero in your calculations, it's basically telling you you've got to rethink this bit or try and work out something new there. There's a few other things as well. So there's also the idea that inside a black hole, you can generate something which a physicist calls a closed time-like curve. And what that means in kind of like non-physicist speak is time travel. That inside a black hole, you could travel backwards in time. And the trouble with that is that violates a whole bunch of basic physical laws, one of them
Right.
being conservation of energy. And as soon as you violate conservation of energy in a physics setting, scientists tend to start jumping up and down and going, hey, you cannot do that.
Right.
And so I'll try and summarize, because the baseline problem is we know these things must exist. They are out there. We have a few possible theoretical models, one of which, the Kerr model, works extremely well in some settings, but the trouble is that inside black holes, it makes predictions that are just downright weird and are either saying to us that we just don't understand science in the way that we think we do, or, and I would say probably more likely, that there is some deeper, more complete description of these objects, theoretical description that is, that we haven't discovered yet.
But
And
basically, it's not a solid object, right?
well, probably not. I mean,
Okay.
there are some alternative models for black holes that say they have what you could call a solid surface. The
Gotcha.
trouble is they aren't distinguishable from the models for black holes where they don't have a solid surface by any experiment that we can currently do. And because the model that doesn't have a solid surface, the Kerr model, because that model works really, really well for all experiments that we have done so far, scientists tend to stick with it because, hey, it works. But we don't know for sure that it's true because, as I said, these weird predictions that are made. And for that reason, ultimately, I have to say, we don't know for sure what a black hole is. They're still deeply mysterious objects.
So indeed. Yeah, I like that, man.
Great stuff. Great stuff. Before I get to that, I'm going to move to Barrick, though, because he's been waiting a very long time. And I know he has some very interesting questions. So, Barrick, if you're there, I'll let you go ahead and ask your question. Then I have a very important, interesting question from the chat that we're going to get to, Dr. Farrah.
I'm sorry. You didn't show up, so I thought I should come to you.
Hello.
Hi,
Hello.
Barrick.
Hi, Dr. Farrah.
Hi.
And peace to the chat and to the panel. I had a question. So your research indicates that supermassive black holes in elliptical galaxies may experience preferential growth chambers. Can you tell me what factors contribute to these preferential growth chambers, and how does it affect the overall assembly of galaxies?
Sure. Okay, so first let me say I should offer you an apology. I didn't realize you were waiting so long. I rambled on a lot. I hope you weren't waiting too long. And secondly, that is an inside baseball question. I wasn't expecting a question like that. Like, okay, cool, but I'm totally happy to answer it. Okay. First of all, let me set the scene a little bit. So, when we look at galaxies in general, if you look at our galaxy and indeed any galaxy that we have observed in enough detail to make this statement, what we invariably find is that in the center of those galaxies is what's called a supermassive black hole, where the word supermassive is just a shorthand way of saying a black hole above a certain total mass. And that total mass is kind of debated. There's no hard and fast definition, but roughly speaking, a supermassive black hole is often defined as being a black hole that is more than 100,000 times the mass of our own sun. Mm-hmm. So just because, hey, you got me on black holes, I'll have a very quick digression. This is one of the many, many things that makes the black holes that are out there in space so deeply, deeply weird, because black holes are one of the few things that we know of where the same type of object can vary in size, or vary in mass rather, by such an enormous factor. So I'll give you, to give an analogy of this, if you imagine the tallest human ever versus the shortest human ever, the tallest human ever, I think, was 8 foot something. So there was some guy who, I can't remember his name, but the world record holder was some guy, he went over 8 feet. And the shortest human ever is like maybe 2.5 feet. And if you look at the difference in those two numbers, it's like a factor of 3 or 4. And if you look at the sort of the thinnest human versus the fattest human, the difference is a bit bigger than that, but maybe a factor of about 10, maybe a factor of about 20. If you compare that to black holes, the smallest black hole that we have ever measured is maybe about, well, the number's debated, but say maybe 3 or 4 times the mass of our sun. And the biggest black hole that we have ever measured is something like 30 to 40 billion times the mass of our sun. And so you're talking about a difference in mass for black holes from the smallest to the biggest of a factor of about 10 billion. And there's very, very few objects that we know of where that is true. Anyway, but to get back to the question, as I said, all or most galaxies that we know of have a black hole in their centers, a supermassive black hole. And we still don't really know why that is, because there's no immediately obvious reason why galaxies should all have a supermassive black hole at their centers, and yet all of them, or nearly all of them, do. And what makes this even weirder is that if there are more stars in the galaxy, if the galaxy itself is bigger, the black hole at its center tends to be bigger. So I'll give some examples, just because these numbers I happen to know, because I do this. So this is what I really do research-wise. Our own galaxy, the Milky Way, it has a total number of stars of maybe 30 to 40 billion. And the black hole in the center is around about 5 million times the mass of our sun. But if you look at a really, really huge galaxy, like say one of the biggest galaxies we know about nearby to us, which is a galaxy called Holmberg 15A, it's got something like maybe 3 or 4 trillion stars, and the black hole in its center is the one I mentioned earlier, which is about 30 to 40 billion times the mass of our sun. So as you get more stars in your galaxy, you tend to get a bigger black hole in the center of the galaxy. And the reasons for this are, again, deeply mysterious. There's no direct link between how you make stars and how you make a supermassive black hole. There may be indirect links. There may be ways in which a galaxy that's forming stars maybe in some way channels material to its center, which helps to form a supermassive black hole. There are some ideas along those lines. But we don't have a good idea of why this is. So a really sort of hot topic in astronomical research at the moment is, how do galaxies get supermassive black holes at their centers, and why is it that the mass of the black hole seems to scale with the total mass of stars in the galaxy itself? There's some process which is making those two things kind of happen hand in hand a little bit. And that's weird, because a galaxy is much, much, much bigger than a black hole in terms of its length, its size. To give us sort of an analogy, it would be like saying, whichever city you happen to be in, take the total size of that city, like how many miles across it is, and then say that how big the city is or how the size of the city changes directly correlates with how big your local grocery store is, or the one down the street from you. The local grocery store is tiny compared to the size of the city. If you observed that the city getting bigger meant your grocery store got bigger and that process seemed to happen together, you'd probably go, well, hang on, that's a little bit odd. But that's apparently what we see with galaxies and their central black holes. So that's the overall sort of framework for how we try and understand galaxies. So two of the big sort of open mysteries in galaxy formation and evolution. To get to your question, some work recently, which I was actually involved with to a certain extent, proposed that there might be evidence, and I'm being deliberately kind of cautious with my language because this is all kind of bleeding edge research and none of it is confirmed yet. When you do research at this level, you typically do a study, you'll present your conclusions, and then other people might come along and agree with you, in which case the work is reinforced and you might start to really believe it. But then other people might come along and disagree with you, in which case you might go, okay, well, maybe that wasn't such a great idea. And your question is really asking about something at that kind of bleeding edge level. And so I'm going to be very cautious with how I phrase this. But there is some evidence that in certain classes of galaxy, namely a class of galaxy called an elliptical galaxy, which is essentially a galaxy that's pretty old. The stars in it are old. It's been around for a long, long time, several billions of years. There's some evidence that in those particular galaxies, the central black holes are growing faster than you would otherwise expect them to grow. So the galaxy and the black hole are both growing, but the black hole is growing quicker than the average, quicker than the global relation between galaxies and black holes would have you believe that the central black hole is growing. And this is kind of really strange if it's true, because it's not confirmed. But if it's true, you would have to sort of try and think of ways, well, hang on a minute, how the hell do I feed the black hole in the center of the galaxy more than I feed making stars in the galaxy itself? There are a couple of possible ways that you could do that. They essentially revolve around the idea of taking the gas that's in the galaxy floating around between the stars that would ordinarily act as fuel for new star formation, and somehow getting that gas to sink towards the center of the galaxy, where it's much more likely to fuel the central black hole rather than to form new stars. That's one way you could do it, but this is all very bleeding edge stuff. And so the overall answer is I don't yet know, even if that preferential growth you reference is happening. I mean, I personally kind of think it might be, but hey, I'm biased. I was on one of the papers that proposed it. But it's certainly not confirmed. And if it is happening, then we don't yet know why it's happening. So again, I'm sorry, I have to end with I don't know, but it's a very interesting research question.
That was still awesome, though. I like that. Even the research question.
Yeah, that was pretty good there, Dr. Farrah.
Yeah.
Well, it's all been good, but hey, we appreciate it, man. That's great.
Oh, awesome. Thank you.
And we like the insight that you're giving us on the research that's taking place. I think that's important, we appreciate that. I do have
another thing, excuse me, Juju.
Go ahead. I'm sorry.
Another thing we really appreciate is the fact that you don't have a problem
with saying
I don't know. And that seems to be an issue in our community, because a lot of people feel like, well, if you don't have the answer for everything, then nothing you're saying is valid. When nobody has that answer. So,
right.
You know,
Oh, absolutely.
we as humans, we tend to try to fill that gap with whatever we believe.
Facts.
But you know, we over here on the pseudo killers, we appreciate I don't know. We really do. We appreciate that.
Oh, I totally agree. And, you know, as you say, culturally, it's such a difficult thing to say.
Yeah.
But when you come down to the sort of the fundamental ideas of being a scientist, the fundamental ideas of investigating new things,
Mhm.
always when you start a scientific investigation, the first thing you say is, I do not know.
Right.
And some people say it has a bad reputation, but to me, it's one of the most enlightened things you can say, because it says, hey, I don't know, but I want to know. I want to discover things.
Right. Juxtapose that science is to know. So you would like beg the question, but in an empirical way, right?
Absolutely.
Okay. I do have another question from the audience, and
Sure.
I'll preface this question. So there's some individuals in we call it the YouTube streets because I think they're lacking a little bit of formal education or may not have any. No, that's a slight. However, a lot of people like to confuse their science with religion. And a lot of times, our battles as pseudo killers is showing the difference, right? So it's a particular group. They think that electromagnetism is God, supernatural God. So, with that being said, I'm going to ask this question from the Bar Reloaded, another group. Shout out to the Barbarians. And our question is from the singularity with the forces that formed, was electromagnetic force the first or strongest force?
Ooh, that's an interesting question. Okay. Let me just kind of compose my thoughts a little bit.
Take your time.
Okay. I would need to maybe go away and think about that to give a really kind of accurate, well-formed answer. So this might be a bit rambly, but I can come back another time and talk more about this sort of once I've worked out my own internal dialogue a little bit.
Okay.
But I can address it to some extent, I hope. The short answer is it almost certainly wasn't the first force to, if you like, quote unquote, form, and it definitely wasn't the strongest. That said, it's a phenomenally important force because it governs so much of day-to-day life on planet Earth. It governs so much of how we see things in the universe because we see via light, and light is a consequence of the electromagnetic force. It governs so much of why things in the universe do what they do. So, for example, the way that stars shine, it's fundamentally they are powered by thermonuclear fusion, but the way that that energy propagates outward through the star, the way that we see that energy propagate through space, is all governed fundamentally by the theory of electromagnetism. What I suspect the question is referencing is the idea of unification. And what that idea is getting at is the idea that the forces that we see today, the forces that we experience around us, that today seem completely separate and different things, were once upon a time, when the universe was very much younger than it is now, not so separate things at all.
Mm-hmm.
So to give sort of to try and give a little background on this, the way that we understand things around us today is by saying that depending on what regime you're in, depending on what you're doing, different force laws, different ways of explaining what you see happen will come into play and govern how things work. So, for example, right now, I would guess, most of us are probably sitting on a chair. I mean, I'm sitting on the ground, but whatever. It's just so I can be closer to the microphone.
I got you.
But if you're sitting on a chair right now, then the two forces that are kind of governing why you feel what you are feeling are gravity and electromagnetism. Because you're sitting on a chair, you can feel yourself pressing against the chair. That's because in one level, gravity is pulling you downwards. But on another level, the reason you don't fall through the chair and fall through the surface of the earth and sink into the center of the earth is because the atoms that make up you have electrons orbiting them. The atoms that make up the chair have electrons orbiting them. And, we probably all remember what happens if you have two negative particles. They like charges repel, opposite charges attract. You've got electrons in the atoms of the chair, you've got electrons in you, and they repel each other. And so that's why you don't just sink straight through the chair. Depending, I don't know, if this would have come up in science classes, but you may have come across this idea that an atom is mostly empty space. You might have heard like, hey, how big's an atom? And people will say, so oh, I'm sorry. I thought I heard someone say something. You may have heard this idea that like, if you take an atom and you blow it up till it's the size of, say, a football stadium, then the electrons would be orbiting in the outer row of seats, and the nucleus would be a basket of melons on the 30-yard line or something like that. And all of the rest is just empty space. And so you can kind of take those pictures and go, well, why don't atoms just go through each other if they're mostly empty space? And the answer to that is that the electrons in the outer orbitals of the atoms are repelling each other. And so you've got these two force laws saying to you why you don't fall through a chair. Gravity pulls you down, electromagnetism pushes you back up. The two forces balance, you stay sitting in your chair. All of physics in the sort of modern day universe is like that. Whenever you're trying to work out why something happens, you say, what force laws do I need? Do I need gravity? Do I need electromagnetism? And do I need what's called the strong nuclear force, which I mentioned earlier, which is the force that keeps atomic nuclei bound together? It basically stops all the protons, which are trying to repel each other, from flying apart and disappearing off into the middle of nowhere. However, there is this idea that as you go back in time and the universe gets hotter and hotter and denser, those three separate force laws start to become harder and harder to tell apart from each other. And this is getting into very speculative stuff, but there's this idea that there should exist one or maybe two fundamental force laws which take the three force laws I mentioned, electromagnetism, the nuclear force, the gravitational force, and kind of combine them together into a single theory, a single force law that describes both of those, or two or all three of those forces together, and says, well, when the universe was very young, very hot, very dense, you can just treat it as one, maybe two forces. But when the universe expanded and cooled, different parts of those one, maybe two forces become so different looking that you need completely separate force laws to start to explain them. And so a significant branch of research in theoretical physics is concerned with doing this. They're called grand unification models, because they're trying to take these three fundamental force laws and combine them into just one or two and see what that sort of deeper force law would look like. In a sense, it's kind of like the black holes stuff we were talking about. Right now, we have a couple of models for black holes which sort of seem to work, but they have their issues. Maybe there is some deeper, more complex, more subtle model out there, but we just don't know what it is yet. The same is probably true for force laws, that out there somewhere is the sort of a single, deep, more subtle force law to understand how the laws of the universe work on the deepest levels imaginable, but we don't know what it is yet. We know these aspects to that force law: gravity, electromagnetism, nuclear force, but we haven't yet worked out what that deeper force law is.
You know, I'm glad you
Mm.
can y'all hear me?
Yes,
Hi.
loud and clear. Go ahead.
Hey, I'm glad you brought that down, because there's people out there that are claiming, because the atoms are mostly empty space, that we can walk through walls, or we can, somehow do something where a solid isn't a solid. So they'll use the empty space thing to like, but they don't understand the forces that you were just explaining. So I'm glad
And
you
I
broke
think
that down.
they'd understand them when they
You
broke
didn't,
their
Kent.
nose.
No, you didn't, Kent.
What
And no, you messed that up. That it was come on, Barrick, help me out. What was the question? Is there solids in on the quantum level? Wasn't that the question, Barrick? See, you messed that up, Kent.
I ain't messing up.
Hey, but the response though, what you just say, Dr. Farrah, they'll understand when they walk into that wall and break their nose.
Oh man, no. But it was on the quantum level though. That's different.
No, I wouldn't. I don't
it?
know what you're
Wait,
talking
let him
about. I'm
answer.
talking about what I heard other people. I ain't
Okay,
talking about
okay.
nothing
I'm gonna leave it alone. I'm gonna leave it alone.
Yeah.
Yeah, because I'm on the negative, Dr. Farrah. Barrick, where you at? Help me out, Barrick.
You done told on yourself.
No, it's okay. It's not like on the quantum level. I think that's a little different though. But anyway,
Have you heard that though, Dr. Farrah?
he's
Like, people
quiet.
saying that we can walk through walls because there's no real
Oh
solids.
no.
You ever heard that?
I've heard that. I haven't heard that in a long time. I've heard people used to try and say that on the internet. They'd go to Reddit and whatever and make that claim. Oddly, they'll never try and make that claim in real life in front of an actual wall, because I think they would be found out quite quickly. But hey, people on the internet will say whatever they want to say.
Right.
Thank you for that. How much more time do you have? I don't want to keep you that long, but if you got 30 more minutes, maybe. If not, that's fine. We can always bring you back.
Yeah, I can do another 30 minutes or so.
Thank you. I'm gonna ask. I definitely want to get back to Barrett because I know he has great questions. That's not a diss to anybody on the panel, but we're kind of bringing Barrett on the fold of the astronomy show. And he does have a good grasp on quantum physics. He's the one I go to
Gotcha.
when I have a question, because I'm doubling into that. I'm learning, but I also want to do some, how shall I say, audience participation. So I'm going to ask. I want to ask two, but I'm going to ask one for now. Maybe we'll get back to the last one from Laurel. Okay. But Philip's question is, what are some of the known functions of black holes?
Ooh. Okay, so again, that's quite a broad question.
It is.
Yeah. Let me try and. Okay, so first of all, black holes are relatively rare objects. There's not as nearly as many black holes as there are stars or planets. They're definitely out there, but there's just not many of them. Mm-hmm. What they tend to do tends to depend very strongly on how big they are and where they happen to be. So let me, I'll give a couple of examples. So first of all, if we see what you might call a normal mass black hole, so not a supermassive black hole, but a black hole that's kind of, maybe a few times the mass of our sun, then it is almost invariably, not always, but a large fraction of the time, it's found in a system with another star. So black holes tend to be associated with other stars. And so one, if you like, function of those black holes is that they allow us to test certain basic physical principles. So you can test like how do things orbit, but you can also look at these black holes, and because of where you tend to find them, you can draw conclusions about how they must be made. So this is partly why we're pretty sure that black holes are made in supernovae. This is why black holes are made when a very big star reaches the end of its life and collapses in on itself, and the outer layers will explode as a supernova, but the inner core of that massive star will continue to collapse in on itself because the strong nuclear force isn't strong enough to support it, and it will form a black hole. And the reason that we are pretty sure about this is because of where we tend to find these sort of ordinary mass black holes. We tend to find them associated with other stars. And when you factor in that to make a very, very big star, you need to start with a very large cloud of gas from which you are more likely than not to make not just one star, but maybe 2 or even 3 stars orbiting in a system. You can conclude from this very, very, with high evidence, where black holes are made. And so that's one sort of function of them, is that they diagnose how stars work, what the end point of a massive star's life probably was, and it gives us insight into not just how stars behave towards the end of their lives, but also to the fundamental physics that drives these kinds of processes. So just because black holes exist at all, it says to us that the strong nuclear force cannot be the end of the story, that there's something beyond that. Maybe there's another state of matter, where I'm now using the word matter rather loosely because we don't really have good handles on this, but maybe there's a state of matter which some scientists call vacuum energy, which is energy that's associated with space itself, which some have theorized, I mean, this is all incredibly speculative, but some have theorized that vacuum energy could be that sort of final, ultimate barrier stopping complete collapse. So the strong nuclear force supports you up to a point, but if you go beyond what the strong nuclear force can support against, the ultimate barrier to collapse down to nothing is vacuum energy. And so that's one thing that has been theorized, in part because black holes exist. We know they are out there. Flipping to the sort of other scale of things, the supermassive black holes that we find in the centers of galaxies evidently play some important function in how galaxies themselves work, because we don't just see supermassive black holes at the centers of a few galaxies. Every single galaxy of any significant size, where we have observed them well enough to conclude whether or not there is a supermassive black hole in their centers, every single one has shown that there is a supermassive black hole at their center. And this result is now so solid that if someone went out there and found an ordinary sized galaxy, say one like our Milky Way, and they looked at the center of that galaxy and showed conclusively that there was no black hole in that, no supermassive black hole in the center of that galaxy, that would be a kind of headline result. Like, that would be a really, really huge deal, and it would probably be like on CNN as one of their top science stories. It would be that weird. So supermassive black holes have got to be telling us something about how galaxies themselves form, and maybe therefore one of their functions is to act as a kind of, I don't know, route finder, like a pathway to saying, how do you make galaxies in the first place? Now, again, I'm getting into kind of speculative stuff here, but the James Webb Space Telescope has found active galaxies, that is, actively accreting supermassive black holes, really surprisingly early in the universe's history. So before JWST was launched, it was anticipated that you would not find supermassive black holes much earlier than about maybe 900 million years after the Big Bang. So astronomers tend to work in units of what's called redshift. And the higher the redshift, the further back in time you go. And so 800 million years after the Big Bang corresponds to a redshift of about 6.1. Don't quote me on that. I haven't done the calculation recently. However, JWST showed that you find supermassive black holes much earlier than that, maybe as early as 300 or 400 million years after the Big Bang. So more than twice what was originally anticipated. If you want that as a redshift, I believe the highest redshift accreting black hole that we've found so far is like a redshift of maybe 10. And before JWST, that was not anticipated. And this is even more evidence that somehow we're making supermassive black holes far earlier than we thought was possible, and therefore they must play some pivotal role in how you make a galaxy, but what that role is unknown. And so I guess the overall answer to the question is black holes have to play important functions. They must be very important diagnostic tools. Their role, I have to say, is somewhat limited just because there's not all that many of them. But because they are so deeply mysterious objects in and of themselves, and because they seem to be linked to processes which are kind of the boundaries of what we currently understand. So ultimate states of matter, how you create galaxies to begin with, for those reasons, their diagnostic power is probably really, really big.
I'm muted. That's really nice, Dr. Farrah. That was from Philip in the chat. The first one was from, I forgot the first one, but Barbie, Posterius, and then the bar reloaded. I have one more from Laurel Burns.
Sure.
And then we're going to get back to Barrick. I'm going to go backwards, Barrick, Kent, and then Anthony, if we have some time, okay? We'll do it that way. I hope that's okay with the panel. Laurel Burns' question is, where does the universal charge originate in the universe, and what is powering galaxies?
Oh, wow. I'm sorry, could you say I may have missed the first. Could you please repeat the first part of the question?
What does universal charge originate? Excuse me. I'm so sorry. Repeat. Where does universal charge originate in the universe? What is powering the galaxies?
Okay, gotcha. Okay, so the first part of that question, again, that's quite a deep question, because if I understand the question correctly, and Laurel, my apologies if I've not understood this, is that it's essentially asking, where does the idea of charge come from? Positive charges, negative charges, the electrons in atoms having negative charge, protons in atoms having positive charge, that sort of thing. And that's a really kind of interesting question that ultimately I'm going to have to say at the end, I do not know the answer to, because as yet, we don't yet have that sort of complete theory of how forces work. So in physics, we would understand how charges work by the theory of electromagnetism.
Mm-hmm.
And electromagnetism it's certainly not a simple theory. I teach a course in electromagnetism to second-year undergraduates at the University of Hawaii, and it is considered a challenging course because, you have to use calculus to do the math. The ideas are kind of subtle. It takes some thought to get your head around. And but the theory itself is pretty well developed. And if you're interested, if you kind of really like your math, the thing to look up if you want the sort of quantitative description of how electromagnetism works is a set of equations called Maxwell's equations, which tell you how do charges work, how do they interact with each other, what do they do, how does light arise from the motion of charges, all of that sort of stuff. However, electromagnetism is ultimately a description of how things work. It is not a description necessarily of the deeper question of why is it that things work in this way. So I can use electromagnetism theory to tell you how radio waves work. You can build a radio from basic components by using the principles of electromagnetism. But if you look at electromagnetism theory and say, why are there charges? Why is there positive charge? Why is there negative charge? Why is there not a third type of charge or a fourth type of charge? Electromagnetism theory won't tell you that. It'll just say to you, hey, look, you've got two types of charge. They work like this, and here's ways that you can use that to build lots of wonderful and interesting and useful things. To answer that deeper question, why there is charge, would require what we were talking about a little while ago, this idea of a grand unified theory where you take two or more of those three force laws, electromagnetism, gravity, the nuclear force, and you combine them into an overarching, unifying description of how forces work. Because in that overarching description, it might tell you, hey, look, this is why you have two types of charge, and this is why they interact in the way that they do, because they are facets of some deeper underlying idea. But the trouble is, we don't yet know what that deeper theory is. And so to the question, why is there charge in the way that there is charge? I have to say, I do not know the answer to that. There are ideas. There are ways that you can get the laws of electromagnetism and thus the ideas of positive and negative charge from a slightly deeper description of physical reality. The math there gets really heavy, but if you're interested, it's a branch of physics called quantum field theory. But even that, I would say, is not completely developed. There are parts of it that we don't yet completely understand. And so ultimately, the jury is still out. The second part of the question, what powers galaxies? Again, that's a pretty... I could ramble about that question for a long time because it's kind of what I do for a living. But I'll give the sort of the short answer. Galaxies contain a huge number of different sorts of objects. And so there's an awful lot going on in a galaxy. But if you just took an image of a galaxy, some distance away from us, and you just said, hey, all the light that's coming from that galaxy, what's powering it? What processes are making that light appear and travel across space to us? Then it's possible to say that the vast majority, possibly all of that energy, is coming from just two fundamental processes. One is thermonuclear fusion in stars, because thermonuclear fusion in stars heats up stars. They then shine very brightly. The light from stars might heat up the gas between stars and cause that gas between stars to shine quite brightly as well. And there's a whole host of energetic processes that happen there, but ultimately it all stems from thermonuclear fusion. The other process that produces significant amounts of light from galaxies, that you could say powers galaxies, is actually what we were talking about earlier, this idea of matter, of stuff falling towards a black hole. Because it's falling towards a black hole, and black holes are incredibly small, incredibly dense, you can build up incredible speed as you fall in. And if some of that energy of motion, some of that kinetic energy, can be harnessed and turned into light, that light will radiate away, and that is light that you will also see. Now, the details get really, really complicated really, really quickly. You can get really lost in the weeds with this stuff. But if you wanted to reduce it to just like the smallest set of processes possible, thermonuclear fusion and accretion onto black holes would be two of the key processes that produce the lights that we see from galaxies.
Very good. Thank you. I really don't think that's the answer he thought you were going to give, but
Oh, okay. Well, in that case, my apologies, and I'll happily
I
come back
know
another
there's
time.
no need to apologize. Trust me. Okay, so I'm going to go back to the panel, and I'm going to start with Barrick. Barrick.
Oh, hi, Doctor.
Hi.
So my question was, in a couple years ago, you had a study that presented evidence for a cosmological coupling of black holes, suggesting they may contribute to dark energy. Could you elaborate on how the mechanism operates and what implication it has for understanding the universe's accelerated expansion?
Sure. Okay. Wow, that is a most inside baseball question. Thank you for asking that. Okay, so just to set the scene a little, this is really kind of like research at the leading edge, if you like. So it's a very controversial idea. I don't know if it's right or not. It's at that stage where, you know, as with many scientific investigations, you start doing something, you publish some papers to say, hey, look, I found this. Isn't this interesting? Let's see if it's true or not. And then other scientists do studies to try and work out if it's true or not. It's not confirmed at all. It may or may not be right. It's at that kind of stage of being plausible, but not confirmed or disproved yet. So with that in mind, I'll give a little bit more explanation. The thing that we were talking about when you were asking me about preferential growth of black holes in ellipticals, there are many, well, not many, I suppose. There are a number of ways that you can explain this idea that black holes, in some settings, seem to be getting bigger faster than you would otherwise expect them to do. One of those ways, and I stress there are quite a few ways, but just one of those ways is this idea of cosmological coupling. Now, the details of this get really gnarly really quickly, but in essence, the idea would go like this, that black holes, because in the world of physics, they are classified as a type of object called a relativistic object, that they are much more, if you like, in tune with how the universe is expanding than objects that are not relativistic in nature. Now, this may sound like a completely crazy thing to say, but there's evidence that this is not such a crazy idea. So, for example, light, or photons, if you like, as they travel across the universe, they exhibit this phenomenon called redshift. And what that means is that as a photon travels across the universe, it loses energy. It might start off being an X-ray photon, and as it travels across the universe, if it travels far enough, it might arrive at its destination being an ultraviolet photon, or it might start off as an ultraviolet photon and end up, when it arrives at its destination, being an optical photon. The baseline idea, though, is that light, if it travels far enough across the universe, will start to lose energy. And the explanation for this, at least the best explanation that we have for this, is that because photons are relativistic particles, the way in which they move when the fabric of space-time, the fabric of reality itself, is expanding, is such that they will lose energy due to being in that expanding space-time. I'm kind of glossing over the mathematical details of this because they're actually not too bad, but they take a bit of explanation. It would take quite a bit of, we'd have to sit down with pen and paper and go through the numbers, and it would not be a short exercise. But you can show this within the theoretical framework pretty straightforwardly, that light does this. And so the question then that arises is light the only relativistic particle that does this? And this is where things get very speculative and where there's no agreement on this yet. This is still strongly debated. But there is a school of thought that says that black holes, which are the only other very, very relativistic objects that we are currently aware of, that black holes should in some way respond to how the universe itself is expanding. Now, again, this kind of sounds a little bit crazy because light travels across the universe at enormous speed and black holes tend to just sit there. But they are both types of objects that kind of push Einstein's theory of relativity to its limits in how we understand them. And for that reason, they can both be classified as being relativistic objects. The way in which this may or may not happen, though, is still heavily debated. And part of that is because of what we were talking about earlier. We don't yet have a completely satisfactory theoretical description of how black holes work. There are some theoretical descriptions of black holes which say they don't know anything about the expanding universe. They just sit there minding their own business. They don't care that the universe is expanding. You know, they stay home and look after the garden, if you like. And if they did that, it would not be at all unexpected because that's what most stuff in the universe does. You know, planet Earth doesn't care that the universe is expanding. If the universe was not expanding, planet Earth would just sit here doing exactly the same thing. So would the sun that planet Earth orbits. So would other stars. So would asteroids. So would practically everything else in the universe that we know of. It would just not care at all. And so it's perfectly possible that black holes don't care either. The trouble, though, with that explanation is that it's not completely theoretically satisfactory. Because if you say that black holes are completely decoupled from the expansion of the universe, they don't know about it, that sets certain conditions on the theoretical description of black holes which aren't completely agreed upon. There's still significant debate on this in the theoretical physics community. And so there are some models for black holes where you say, okay, they do know about the expansion of the universe, and as the universe expands, black holes, because they are relativistic objects, just like photons, in some way will respond to that expansion. The trouble is, because we don't have that complete theoretical description, we don't know for sure what that response would be. One possibility is that they would gain in mass. They would gain in mass not because anything was falling onto them, but just because the universe expanding kind of made the black hole get bigger too, but in mass rather than size. You could sort of imagine it as saying, as the universe expands, imagine that you're stretching a rubber band. You know, if you stretch a rubber band, it gets tauter and tauter, and you're kind of giving it energy as you stretch it. You could sort of think of it like that as the universe expands, you're kind of stretching or making tauter the inside of a black hole, but instead of getting bigger in length, that extra energy that you're giving it by stretching it is translated as an increase in mass. Now, this is also a deeply speculative theoretical idea. And when you have two speculative theoretical ideas, the best thing you can do is go out there and do an experiment to test which of those speculative ideas, if either, is correct. And this is where things get quite murky because, as I said, this is kind of cutting edge stuff. There are some studies which have claimed that there is evidence that this is happening, that black holes are gaining in mass as the universe expands. And full disclosure, I'm one of the authors that wrote one of those studies. But at the same time, there are studies out there that came along afterwards that said, hey, not so fast. This isn't a straightforward thing at all. It may or may not be true, and there are certain things you're going to have to deal with if you want this to be true. And so at the moment, it's at kind of that stage in the proceedings where a whole bunch of scientists, me included, are kind of having that argument to say, what does the evidence really show? Does it show that this is right, or does it show that this is wrong? Does it show that black holes are gaining mass as the universe expands, or does it show that there's other things going on with them that we don't understand yet that could explain this observation? So the jury is still out, I would say, but that's kind of the state of play of that particular idea.
I mean, I wish I had a that like bomb soundboard for real. The answers to the questions are excellent, Dr. Farrah.
Oh, thank you. Oh, I'm always happy to help.
Yeah, I think like how you're illustrating your answer, we can almost make a visual. Especially those who know a little bit, you can kind of, put it together, and I appreciate that. I think we all appreciate that actually. Kent, do you want to go next?
Yeah. So I know we kind of getting to the end of the
right.
the presentation. I wanted to end it on a good note. So I wanted to ask you, what hypothesis do you lean towards when talking about the end of the universe? Whether it be like the big crunch, the heat death, the big rip. I know there's a couple of them out there that haven't been, they haven't figured it out yet, of course, obviously. But which one do you lean toward?
Oh, wow. Oh, that's you guys asked the deep questions. Okay, the short version is I honestly do not know, and I'm not even sure which way I would lean on that question. Gotcha. But let me explain why. I'll give a little historical perspective on this. As I mentioned earlier, the Big Bang model was kind of triumphant round about 1963, when the cosmic microwave background was discovered. It showed that the universe must have once been hot and small and dense and has expanded after that. And that kind of said, right, we must have a Big Bang, we must have an expanding universe since then. And since then, a lot of the effort in studying the universe has been actually trying to address that exact question, like, what's the universe going to do? And up to about 1997, 1998, the consensus among astronomers was that the expansion of the universe was slowing down as time passed. And the debate at that point, or up to that point, was between two competing scenarios. One where the universe expanded and the expansion slowed down and slowed down and slowed down, and eventually the expansion reversed and the universe collapsed back in on itself, and there was a big crunch. And then the other competing idea was that the universe just keeps slowly expanding, slower and slower, but just kind of keeps gently coasting outwards forever. In 1998, however, evidence came along for this idea of dark energy, which is otherwise known as accelerating expansion. And this kind of just threw a wrench into the gears of everybody, because it essentially said that the universe started off in a Big Bang, expanded really quickly, then expansion started to slow down, and it slowed down for a few billion years, but then expansion started to speed up again. So expansion started to speed up round about maybe 6 billion years ago. It's like halfway back in the history of the universe. And this was a hugely problematic discovery in many ways, because nobody had any good explanation for why this should be. There was no kind of already understood theoretical principle that meant you could say expansion would slow down for a while and then suddenly start speeding up. There was no stuff in the universe that we could see or study that said this would happen. There was no sort of theory that people had agreed upon beforehand would predict this phenomenon. It was deeply strange. And really, astronomy or cosmology, since around about 1998, a very large part of it has been dedicated to trying to answer this question. What's dark energy? What's making the expansion of the universe accelerate for the last few billion years? And the trouble is, no one has a clue. There's been lots of work done. I mean, when I say nobody has a clue, that kind of sounds like maybe I'm being a bit rude, but I'm honestly not. It's an incredibly difficult problem.
Right.
And a lot of people have been studying it very hard. The trouble is that as yet, we have not yet had that sort of decisive breakthrough that's revealed the answers to us. We've studied lots and lots of possibilities, and either we've discovered that they don't work, or that it's very, very hard to make them work, or very, very hard to prove conclusively that it uniquely works. And so we're kind of in this position where there's a bunch of theoretical explanations for why dark energy is there, but we don't have a clear picture of which, if any, of those theoretical pictures is the correct one. And this is why I had to say at the beginning, I don't know, because some of those theoretical pictures would predict a big rip. The universe expands faster and faster and reality tears itself apart, maybe.
Right.
Some of those pictures would say dark energy will turn off and the universe will just continue coasting and, will expand forever, but slowly. And other theoretical explanations say, well, dark energy will reverse what it's doing,
Crunch.
and you'll have a big crunch.
Right.
And nobody knows which it is. There is, I'll give you a sort of really, really recent study. There was a very, very recent set of papers, academic research articles that were published by a collaboration called DESI, or the Dark Energy Spectroscopic Instrument. And they have found tentative evidence that dark energy might, and I stress the might, because this is all, the front line of research, if you like, that dark energy might be thawing. And what that would mean is that dark energy is starting to fade. If that's true, it might, you can tell I'm not sure about this because I'm adding all these qualifier words.
Hey, look, you ain't making no claim.
I'm making sure I'm making no claims here. But if it's true, then what that might mean is that we won't have a big rip.
Right.
Maybe. So if you held a gun to my head and forced me to make a prediction, I would say probably not a big rip, but I wouldn't like to pick between slow expansion forever and a big crunch, because there's just not enough evidence to say which of these even could be correct.
Gotcha. I like the heat death one because it seems like everything gonna run out of, the energy gonna burn off on everything. But that's just my guess. I ain't making no claim either.
That's certainly plausible given what we currently know.
Right. Appreciate that, man.
Okay. You have time for one more question or two more?
I'm sorry, it would have to be one more. I'm sorry,
That's
but
fine.
I could definitely do one more.
That's fine. I pushed it a little bit. That's fine. Thank you.
Well, yeah,
do I
you
need
did.
To
Where we at?
do I need to do a coin toss between Anthony and Unc?
I don't want no question. You know what?
Yeah.
I'm gonna save my question to the next time.
Okay.
I'm good. Yeah, we got.
All right,
I'm
we'll
good.
save it to the next time.
Yeah, I'm good.
So,
I'm straight. I appreciate it.
So I just want to say this for the chat. I've taken pictures of all the questions that were dropped in the chat that I didn't get to ask. So when Dr. Farrah comes back, because you are coming back, right, Doc?
Oh yeah, sure.
Oh yeah.
He's
So-
never coming back
tomorrow at 8 p.m. Dr. Farrah.
So, we'll probably start with some audience questions. Of course, bring back
okay, crazy.
Barrick, because he is very insightful. Puppy.
I can't stop laughing. Something is wrong with that man. King Dolo.
I'm just messing with
And no, he definitely due diligence in your research, and I think that's pretty awesome. So I would love to hear more of that dialogue. I might even get Barrick his own time with you, Dr. Farrah, so y'all can have like a back and forth. That would be interesting to see, because you've done it so many times with us. But we so much appreciate you. You are a professor, so that means you are a teacher by profession, but it also shows in your heart how much you're a teacher, how much due diligence you take to bring these concepts down and to communicate them effectively to people that don't have much knowledge. That would be me. So over and over, we appreciate your time.
Oh,
And we appreciate your
Yes,
effort and
indeed.
your energy. So thank you. And we'll be scheduling the next show soon, because I know you're on break. So I'm gonna try to get you in as much as you would allow for this summer, so we can cover a wide range of topics and have a nice catalog of pseudo killers and Dr. Farrah. So
Totally.
thank you again.
And I appreciate you guys too. It really is a pleasure to talk to you guys. It's great.
Thank you. So you're free to go, but I do want to say, because I know your time. It's what time is it? What time is it? In Hawaii? I ain't gonna ask that, but here's
late in the morning time. It's about
you're right.
trying to get breakfast.
But shout out to the chat. I think we had some great positive feedback, and I love that. So thank you. I'll make sure that when we do the next show, I'll put out, a short, everybody. So just keep up with pseudo killers, and we'll bring that back sooner than later. Like, we'll try to do it within the next month. Let's do it like that, because Dr. Farrah is enjoying his summer vacation. So and for people interested, he does have research out there. I can, if you ask me, if you're in the Discord, if you ask me anywhere, just like message me and I'll get you those links. We do have those. And he also teaches at the University of Hawaii at Manoa. Still, right, Dr. Farrah?
Yes, that's right.
Okay, so you can also look him up and find his research doctorate that way, or just by his name. But if
real research too.
Yeah.
Not the YouTube acting like you don't research
already.
Real professor.
No.
Real scientists.
Real
science. Right. So
y'all play too.
Y'all is funny. I cannot do that.
Dr. Farrah, you don't know we be going through it. We got people popping up acting like they scientists, acting like they professors.
Oh, boy.
I'm like, that's not how a professor normally.
That's not how it works.
When you ever hear a professor or a scientist say, they will say, you know what? I'm not an expert in this.
Facts.
Right? If it's a question, you'll say, well, I'm not prepared. That's the red flag when people come on here and they know everything. That's the difference between a real expert and a professor, right?
Facts.
And the person just talking. Know everything without just know everything. That's the clarity right there. So let that be a little key to y'all. When you're talking to people and they answer every question on planet Earth, they pseudo. Absolutely.
Right.
Appreciate it. Yeah.
That is so true.
Yep.
He said that is so true. Flipped. So with that said, we're not going to take up any more time. Y'all have a great night. You already know how I'm going to end. So until next time, peace, y'all. Thank you.
Peace.
Shout out to all.
So go ahead, get it real quick.
What's good? What's happening? A well-organized lie. A well-organized lie. It beats a disorganized truth every time. For who we?
A pseudo gon' die, they saw a pseudo killer. I'm a pseudo killer, intellectual sunslinger. I'm a pseudo killer, intellectual sunslinger. I'm a pseudo killer, intellectual sunslinger. Pseudo gon' die, they saw a pseudo killer. I'm a pseudo killer, intellectual sunslinger. I'm a pseudo killer, intellectual sunslinger. I'm a pseudo killer, intellectual sunslinger. Who do you believe in? People bringing misinformation when that information ain't disinformation. That's disinformation. Gotta know the difference in information. Get information with the pseudo killer army hunting pseudo. Cause you gotta train your mind to fight against them pseudo judo. People with the scholarship salute, we give them kudos. But the people with that look of shit, we look and see straight through those like telescope. If you ain't speaking fast, we gotta tell them folks and let them know the of it. You bringing malinformation to blacks, then you the Ku Klux. Like say, don't talk me to death, bro, what the proof of? Good choo-choo chillin', why you wanna go way bad choo-choo up? Boy got the tank in the cut. I'm in Sosa World plotting on the kick though with Kent. Come in Tiffany gave me the pseudo names on the list and said went and got the low. Anthony got him in the scope, Gullah and Gozy make sure DNA ain't a problem for them folks, cause a pseudo gon' die at the source.
Anthony,
I'm a pseudo killer intellectual sunsling, ayy. I'm a pseudo killer intellectual sunsling, ayy. I'm a pseudo killer intellectual sunsling, ayy. Pseudo gon' die at the source. I'm a pseudo killer intellectual sunsling.
What you want to say, Bobby? Get it in. We can hear you now. I got it.
Hey, man, y'all know what it is, man. Y'all listen to Space Beyond, man. Space Age African. Y'all know what it is. We here. Take you from the Stone Age to the Space Age to the thinking, man. Yeah. Staying tight with the experts. Staying in conversations. Big up to Anthony. The only one with a real telescope. We don't got the pseudo telescope. We got the real telescope.
Okay, I'm Jim
Army
Express.
on the building. We all here, man. Yeah.
Good night, y'all.
Peace.